Section 16.5 talks about surfaces and areas, and we start by recalling that we defined curves in the plane in three different ways. We used explicit form, that's y equal a function of x, implicit when we get a 0 on one side, everything else on the other side, and parametrically. And we're talking about something like y equal f of x, right? A curve in the x and y. Now, when we get to spaces, we define z to be a function of x, y, and z. Now we're talking about something slightly different. Let's say a plane. And implicitly, we have f of x, y, z, kind of like when we did in parametric equations. But if I want to represent it by using a parametric surface, well, here I have to really define r as a function of u and v, because I don't only have one unknown to worry about, I have two unknowns to really worry about, right? So if I looked at the shadow of this, that will fall on a line. If I looked at the shadow of this, that will fall as an area. And to trace an area, one unknown is not enough, I need two. So this would be a function of u and v in the I, a function of u and v in the j, and a function of u and v in the k. Right? That's kind of to represent such a surface. If I want to pinpoint a location on it from the origin, well, I need to know how to move on the x and the y. The shadow of this is 2 dimensions, which requires a u and some v. Now, if I was given y equal f of x, well, r of t is very easy to come about. R of t will simply be t f of t, or if you like, you could simply say r of x is x f of x, and let x vary between such and such. And now if we have z equal f of xy, well, I could say r of u and v would be u, v, and f of u, v. Or I could simply say, you know what, forget that. I'm just going to find a function in terms of x and y instead of u and v, and that would be x, y, and z, which is f of x, y. So something we really have to get used to. Not very pleasant, right? And if I was looking over a specific r of u, v, that would be the domain associated with that graph. If this is the u function, and this is the v function, and its surface, same thing. Now I want to practice a few problems. So if I look at the first example, find a parameterization of the surface. Find me like a vector, so to speak. The key is for you to visualize the graph and figure out how you're going to do this. You know this is z equal 9, and that's going to cross at 3 and negative 3, right? And the graph is going to look something like this. Well, I know how this works. If I am to really look at r and I could call it r and theta, right? And I could say, you know what they want above the ground. Okay, if that's bigger than that's a solid, I'm gonna call x to be r the cosine of theta and y to be r the sine of theta. Why is that? Because when I look from the top down, I only see the two-dimensional circle, right? And the reason I'm making only 3, if you say 3, you're only getting the shell. This says z is bigger than or equal to 0, z equals 0, 1, 2, 3. It's going to take on all the values, which means I want r to be between 0 and 3. What's the difference? I want all of that solid. And I want theta, obviously, to run from 0 to 2 pi. That's perfect. I get the floor. And now I'm looking at the z. What do you think z is going to equal? Well, wouldn't z equal 9 minus r squared? Because that is x squared plus y squared. And with this restriction on r, I'm going to really get it to be the solid desired, or the desired solid. Number 4 is the next problem. The portion of z equal 2x squared plus y squared. Well, let's see. Z equal 2x squared plus y squared. The graph is not needed, that a must if you can visualize it. If I zero the y, z equal 2x. Z equal 2x. Right there. And z equal 2y. It's like a code, so to speak. And I'm gonna cut this from z equal 2, z equal 2 to z equal 4. So I'm looking only at that portion of the code, sort of something like this. Well, how am I going to describe that? R of u and v. Well, you could call them u and v if you want. You could call them r and theta if they're circular. That would be wiser. R equal r the cosine of theta, y equal r the sine of theta. Reason for that: cosine squared plus sine squared, that will give you simply z equal twice r, and that saves you a lot of pain on the long run. All what I have to do is make sure that if I put a 2 right there, then I'll get 2 equal twice the square root of x squared plus y squared. That is 1 equal the square root of x squared plus y squared. That is 1 equal x squared plus y squared. That's a circle with a radius of 1. And if I put a 4 in there, I will do the same. I'll get 4 to equal twice the square root of x squared plus y squared. And if I solve this, I'm going to get x squared plus y squared to equal a 4. Divide by 2 and square both sides. So I need r to run between 1 and 2. That will do it. Looking from the top, that's what I'm going to see. 2 circles, one with a radius of 1 and one with a radius of 2. And I need theta to run between 0 and 2 pi. And that takes care of the whole solid. The next problem on the list, this is a sphere in the first octane between the xy plane, the floor, and z equal the square root of, that's z equal r squared, right? So that's like a cone, but in the first octave, that's this, this, and cut off on those two. There. So if I glance at this, I'm thinking x squared plus y squared plus z squared equal a 4. X squared plus y squared plus x squared plus y squared equal a 4. that is x squared plus y squared equals 2, right? That's where those intersect. So this is, remember, a cone coming from the top down, and that's what it's going to match. And now if I call this r of r and theta, I could use u and v again. R the cosine of theta, r sine of theta, because that's when they intersect. I'm going to see r to be between 0 and radical 2, and theta is going to run only in the first quadrant, right? And what? And this would be the square root of, let's see, what does z equal? Square root of 4 minus x squared minus y squared, r squared, right? And I'm going to have r run from, oh crap, r is going to run from the square root of 2 to 2. If I look at number 10, I'm looking at the surface cut by y equal x squared. So I could look at that graph. I really don't need the graph for this one, but let's look at it anyways. Y equal x squared. Y equal x squared. Let's run on the y-axis. Z equals 0 is the floor. Z equal 3. And x equal 2. And y equal 2. I'm sorry. There. Something like this. Right? Well, I could say in this case r of, and I could say, look, z is fixed. So I could say z, let z run between 0 and 3. Use cylindrical coordinates. I'm sorry, not cylindrical, yes, cylindrical coordinates. And I could say, look at this, let this be t. If x equal t, doesn't y equal t squared? I could call it x. I could call it x and x squared. That's the same thing. If I call this x and this x squared, well, no matter what you call it, either you call it t and z right there, you could call it u and v, and there's v, right? Again, it doesn't matter what the letters stand for, as long as they mean the same thing. Now, how are you going to figure out the values? Well, we let this be t. If y equal to 2, that means 2 equal x squared, x equal plus or minus radical 2. So if x varies between negative radical 2 and positive radical 2, that would do the trick. If you called it t, t would vary between plus or minus radical 2, whatever works. Okay, last problem I want to look at before, again, not the last problem of the section, but for this homework. Portion of a cylinder above the xy plane between x equal negative 2, so 1, 2, 3, nope, 1, 2, 1, 2, 1, 2, so something like this, and it runs between negative 2 and z equal 2, so something like this, right? So a cylinder, I could say, well, let's see, r of, it should be r and theta, but there's an r there that's kind of confusing. Well, it's fixed, it's the shell, right? So I could say that is twice the cosine of t and twice the sine of t, and let this be run at t, and let t run between, let's see, I want to have 0 to pi, right? And I could call this y if I really want. The book doesn't like that at all, and I could say y varies between 0 and between negative 2 and 2. Most likely